All right, guys, congrats on finishing midterm 1. This is worksheet number 6. We're going to be focusing on magnetic force and field. So there's a few right-hand rules. I'm just going to call them right-hand rule number 1 and number 2, as you see labeled in positions number 1 and 5. Numbers like 1, 5, and 5 right here. And, some people do the right-hand rule in different ways. Some people use their forearm. Some people use their older fingers, whichever way you want. I think the classic way is kind of the thumb and the pointer and the middle finger way, as shown in that one. And then there's the other one, which is where you put your thumb in the direction of the current and you curl your fingers. But we'll talk more about that later. We can find the magnitude of the electric field through a current I, just through that equation, that mu naught I over 2 pi r. And then the force on a charged particle moving in a magnetic field, that equation is not going to come up on this worksheet, if I remember correctly, but it will come back up on the homework. And it is like a really good question if you want to think like centripetal acceleration. And then we have magnetic field of a point charge, right-hand rule number 2, which we talked about and we'll review more. And then we have magnetic force on a wire. And kind of the key thing to realize with these either magnetic force equation, that being number 3 or number 6 here, is that they're cross products. So what's a cross product? It's a binary operation of 2 vectors in 3D space. So it's basically when it's like not, although they are being multiplied, that cross there more tells us that it's actually ILB sine theta, where that angle theta is going to be the angle between the 2 vectors. Lucky for us, though, that vector is always perpendicular. And we know that sine 90 in this case is going to be equal to 1. Right? Yeah. So I think we can jump into the first set of questions here. So in part 1, we're asked to determine the direction of the force and the magnetic field on a negative charge for each case shown in the figure. So part A, we're looking for that magnetic force, and we have the velocity. So this is a right-hand rule kind of setup here. So I pre-drew all of these before, so I don't spend 600 years drawing. So let me do this, duplicate. And by the way, every drawing in this worksheet was hand drawn. So if I hear a single complaint, I'll lose it. No, I'm kidding. So right-hand rule, how does it go? Let me see, which camera is on? Is the class camera on or is my camera on? Okay, so, you do I start with my pointer finger. I go the direction of the velocity, middle finger, the direction of the B field, and then thumb will tell you how the direction that your force is. But remember, we're dealing with a negative charge here. So when I set it up as such, I'll see I'm pointing to the right with my thumb, but because it's a negative charge, it's actually going to be going to the left. So I'll draw FB going leftward in the question. So again, pointer finger in the direction that the velocity is going, middle finger goes into the page because cross means into the page. My thumb is pointing right, so it's actually going left again. And now my pointer finger is going into the page. My middle finger is going rightward. My thumb points down, but remember, negative charge, so it's actually pointing up. And then, at this point, it's going to be pretty much the same thing, thumb pointing up. So it goes into the page in this case. Just with a negative charge, you just flip it basically. And then pointer finger, middle finger up. Again, thumb's pointing up. So it's actually going down here, FB. Okay. And then this next one was kind of to just give you a little, I don't know, it's called a reality check here. And it's to remember that you can also solve using your thumb and your pointer finger, right? So if your pointer finger is pointing up like this, wait a minute. Yeah, and we're dealing with a negative charge again. So our thumb's pointing up, but in reality, it represents the FB that's pointing down. Pointer finger is pointing out, and our middle finger is pointing rightwards. So our B field is going to go to the right. And this guy, and using this kind of equation is really important, especially when you have like an electron. I'm just going to draw it out just because, and let's say it's like an arrangement like this, right? And if you have an electron moving down this way, you only know the direction of the B field. Well, I kind of gave it away because I knew how to solve it there. But if it's moving in this trajectory, we call that FB. and we know its velocity is this way, and we know the B field will have to be pointing up in that instance, right? And that's what allows it to move on this circular trajectory. I think that's a question in the homework, so that's a little nice hint beforehand. Okay, so this next one, like this. So my middle finger is pointing into the page. Question 3 here. So FB is pointing down, middle finger is pointing down, this. And then this last guy, and my middle finger is pointing into the page. Okay, so I mean, this is just a good way to test yourself. The reality is, like, if you're confused on this, I would really need to see you in person to kind of manipulate our hands together. So here's just the answers for this one. There's just kind of practice this one and get good. If any questions, let me know. I'll pause and take questions. Okay. Okay, so we can move on to question number 2. I guess an important thing to remember is just when you use this right-hand rule, remember that all your fingers need to be mutually perpendicular. That means there's going to be a 90-degree angle between every single one of them. Okay, so let's look at question number 2. Here we have 2 thin wires, and we have them in this arrangement that is so well drawn. Thank you to whoever drew that. And we want to determine the magnetic field at point A and then also at point B. So let's just start with A. Again, I pre-drew these, so I think it'll be quicker to just duplicate it. All right, and this is question number 2. It's question number 2. So here we have a different right-hand rule. This is right-hand rule number 2, where you put your thumb the direction the current's going. So in both cases, my thumb is like pointing out of the page, and you curl your fingers. And the important thing is you go between where the current is here, your point of interest, and you will always draw a vector that's perpendicular to the shortest distance between them. So that, you know, what's the shortest distance? It's always going to be a straight line. So my thumb's pointing out. That means my fingers are pointing up. So the perpendicular line that exists here, let's call this B1. Okay. And then same thing is I put my fingers up, I curl my fingers, go that distance. The only way I can point is point downwards. So that's always a little confusing, but I don't know. It's kind of hard. Yeah. Okay. Oh, I could go up to this.
Are the eyes, are they pointing out at us?
Yeah.
Okay.
Laser, like what I remember is like, this looks like a laser, right? When I point a laser at you, it's going to be pointing at you. So that's how I remember that. And X goes into the page, like on a map, you draw X marks the treasure. So you curl your fingers. So you put your thumb in the direction the current's going, it's coming out. You like curl your fingers basically, I don't know, 90 degrees. You take the shortest distance to the point of interest and it's pointing up. And then same thing here, or it tells you the way it's curling there, right? Because you can imagine this field thing is a big circle. This goes like, right? So my thing is curling this way. So at this point, it needs to be perpendicular, it's pointing up. And then over here, when I go like this, you can see my right hand is now curling down. So what's the perpendicular that's on the shortest distance? This is the straight line, it's pointing down. We good?
Yeah. The triangle, those aren't wires or anything. Those are just distances.
Yeah. This is the wire.
Okay.
It's coming out of the page. Like 2 thin wires are like coming out of the page. Okay. Yeah.
This one by B2 is down.
Yeah, because when you, I'm going to draw this first. Okay, so you put your thumb out like this.
Yeah.
Your fingers curl this way.
Mhm.
So that means this one's always going counterclockwise, right? Always going counterclockwise. So it's going counterclockwise. At point A, if it's going counterclockwise, which way is it going to be pointing? Below this line or pointing upwards, like B1? It's going to be pointing down, right? By definition, it always needs to be perpendicular to the shortest distance between them, which is that straight line. So perpendicular means 90 degrees, right?
Yeah.
So that's why it's got to be pointing straight down. It can't be down like, it can't be like this. It can't be like this. It can't be like this. It can only be like this. It has to be 90 degrees.
So perpendicular at that point you're trying to reference.
Yeah,
Okay.
and basically this only tells me, when I do right-hand rule number 2, it tells me the direction the vector is gonna be pointing at everything to the left of that position. Right?
Mhm.
So. Cool. Late. Out. No. All right, so we're good with that one. This one's also very important. Like I guarantee a question like this on the exam. And then for calculating your B field, we just got to use the equation that they gave us. And to calculate B net here, I'm going to write B2 minus B1. Wait, sorry. Minus B1. And let's first draw a coordinate system. I'm going to draw it this way because I can see something already. Oh, geez. And the reason why I draw B2 minus B1 is I know B2 is going to be bigger than B1 because I1 is bigger than I1 and everything else between them is constant, right? That mu naught is constant, the 2 pi constant, and the distance between them is both x over 2. That's that distance from here to here. That's the distance from here to here. Okay, so that's why I'm doing B2 minus B1. You know, you're going to plug everything in. I'm just going to factor out. Distance between them is x over 2. We already know what x is. I2 minus I1. Plug in everything, solve. B net is going to be equal to. Oh, sorry, I just put my big face into the camera. It's going to be equal to, how many zeros is that? 5 zeros? 1, 2. And then what's going to be the direction of this vector? I kind of gave it away already. Which one's bigger, B2 or B1?
It's down.
Yeah, it's down.
B2
Wait,
is
so what
bigger.
should we evolve into B1 minus B2?
I mean, your magnitude would be wrong.
Do the absolute with that and
Yeah, I guess I would say just, but it's easy to remember. Just look at the one that's the bigger current. Yeah. So I'll even say that. I'll say, because I2 greater than I1. That's part A. All right, any questions on this one? And now if we look at part B here, this is more how you guys are going to see it. We're going to be looking at this point P, and we're going to obey the same rules. So now, Hannah, what would be the direction of B2 in respect to part B?
Direction of B2.
Mhm.
Sorry. Oh, this is the curling one, not the.
Yeah, this is right-hand rule. Whenever it's a thin wire, it's right-hand rule 2. But no one say I want Hannah to do it. What is the direction of the B field
Okay,
for part B at point P? And we're looking at, and you were worried about I2.
okay.
Look at the first page. Wait. Which right-hand rule are we using? Which right-hand rule are we using? Okay, I'm gonna say this. When we're dealing with thin wires, we use right-hand rule 2. That's the thumb out, finger curl. We can only use this one when we have a velocity, right? We can only use right-hand rule 1 when we have a velocity. Nothing's moving right now. We just have wire 1. Okay. Actually, it might be easier if you come up. Come on.
So, okay, right hand tool is the one when you're wrapping it around, right?
Yeah, so which way is the
Okay.
wire going?
So if this dot means what, out of the frame?
Out of the page.
So
Yeah.
you're going counterclockwise.
Okay, so show me which way it's gonna go. Put your
I'm
hand on the
scared.
thing.
Okay. what
And
is
which way is your thumb going?
that way?
Well, no, it's
Wait.
coming out of the page. So which way is your thumb going?
Oh. If this is out of the page, isn't it it's not rotating counterclockwise?
It is rotating
Okay.
counterclockwise. Okay, so then what's the direction of the B field?
Oh, up. Or no? I'm so
Take your time, take your
confused.
time.
Wait, okay.
1 second. Sorry. Okay. So for B1 now, we just find that shortest distance between it, which is that straight line, thumb pointing up. We know we're going to be, again, perpendicular. So it's perpendicular here. That means 90 degrees. This is B1. And now you'll kind of see why I define my positive x direction as pointing this way, because both of my vectors are pointing towards the side. So I just like to work with positives, did it that way. The next thing is we need to break this guy into its components. So for B1, we have a sine component. Let's call this theta right here. We have a sine component this way. So B1 sine theta, cosine component, B1 cosine theta. Okay. And B net at position P, we know that's going to be B net x squared plus B net y squared. Square root those guys. And we can just start working this problem out. So let's start with the x direction, B net x. What's in our x direction? We have B2. That's why, again, I put my coordinate system going this way. So it's plus. So that's plus B1, yikes, B1 cosine theta. And now you just got to plug in, factor everything out. I know that mu naught is going to come out, that 2 pi is going to come out. What we're left with is that I1 over R, and we'll call this R, plus I2 over Y. So we don't know what R is, but you can just calculate R by Pythag. R is equal to 0.22 meters. We don't know what theta is, but theta can just be found with a tan theta equals 0.1 over 0.2. So theta is going to be equal to 26.6 degrees. And at this point, I forgot a cosine theta somewhere. Right here. It's just this is theta too. Because it's the same triangle, we just rotate it 90 degrees. Sorry, this should be it. Because by definition, it's the same triangle. Because like the vectors are, everything's perpendicular with respect to each other. So it's the same thing, just shift it. Yeah. And B net x, we get as 0.1234744 t. Okay. And then B net y. And what's the only thing in our y direction is that B1 sine theta. You're just going to plug in everything for that guy. Comes out to be equal to 0.0001222 t. And then we can just plug in both of our values into this expression. B net P is equal to 0.0000754. And plug in your two components to find the angle for this vector. Call that alpha, and alpha will be equal to 9.3 degrees above positive x-axis. I think this gets to all the key ideas here. Okay, let me zoom out here. All right.
Question. How did we solve for?
All right, so now for question number 3, we have 3 thin wires as arranged in the diagram. We know each current, and whenever we see these thin wires in a question, that tells us we're going to be working with right-hand rule number 2. So let's work this guy out. Let me put a pause real quick and allow everyone to try this out. Okay, so just to recap what we did, we have I1 going into the page because our fingers curl in on the side of P, I2 going out because our fingers curl out on the side of P, and then I3 also going out for the same reason. So now we just have to define something as positive, right? So going into the page or out of the page is positive. I can already tell if I want to work with a positive number, I'm going to say going out is positive. So I'll write, I don't know, out is positive. Okay. So then we write our B net equation, And in this case, they're all pointing, within the same axis. So what we call out or in. So we can just find the sum of each one. We have B3 pointing in the positive direction. We have B2 pointing in the positive direction. We have B1 going into the page, so therefore it's negative. At this point, it's all pretty much what we've done before. I'm just going to factor out that mu naught pi. What we're left with each one is its relative current, and the distance it is away from that point P. So for I3, I wrote it wrong on the key. I was like, wait, what? So 0.2 for I2, it's going to be 0.6. And this last guy is going to be 0.7. Oops. Minus I1, which is 0.7. Plug everything in, work everything out, and that's going to be 0.00054 t, and that's going to be units. That's going to be units t, and the direction is out of the page. And just to remember this mu naught value, I guess I haven't said this yet, that's going to be equal to that 4 pi times 10 to the minus 7. And and these pi's cancel out. So it's always pretty convenient to just do that. Okay. And that's number 3. Oh, that's number 3, part A. Oh. And then for part B, we want to determine the magnetic force on the wire with the current I3. So what's the magnetic force here? Okay. So let's first find the direction that it will be pointing. Okay. So here we have I3. Well, I guess I have to solve for, you should solve for B net first. That makes more sense. So B net at position I3. So at I3, let's keep everything, let's keep positive going out. We have I2, which is going out, and then I1, which is going in. So that's going to be a B2 minus B1 situation. And, at this point, this part should look familiar. Plug everything in. You get 0.0000. That's 4 zeros. 66 t. And we're going out of the page. Okay, so now let's call this B part 1. For part 2, we need to solve for the direction of that force and the force itself. So what's our equation for that? That's going to be FB equals IL cross B. Well, we know the cross product is going to be 90, so it's going to be sine theta, where theta is equal to 90. So we can just rewrite that as I3 LB. Okay. So plug in everything. We know that's 50 times the length of this, it's 0.5. And then times that B net I3 we just got. I won't rewrite it, but you know what to plug in there. Okay. So if you draw what we know here, we know that B net here is going out of the page. Okay. So to solve for the direction here, you do right-hand rule number 1 with a twist, that being the direction of the current is the direction your pointer finger goes. So pointer finger is pointing straight down, your middle finger is pointing out of the page, and my thumb is pointing to the left. So that means this guy is pointing out this way. So FB. So then this whole thing comes out to be equal to 0.000165 newtons left. One second. Ooh. Okay. Pausing the recording. Okay. And sorry, I forgot to write this in the question. The length of the wire, so L, is equal to the 0.5. Yes, the length of the wire is 0.5. So I'm gonna write that big up here. L is equal to 0.5 meters. Sorry, I forgot to write that. And that means this L, this guy right here, is equal to 0.5 meters. Sorry about that. Okay. Any other questions on that one? Yeah. So question 4, we have 3 thin wires. They are arranged as they are shown in the figure. We want to determine, in part A, we want to determine the direction of the net magnetic field. So net magnetic field, we could actually figure this out right off the bat, qualitatively. I'm going to pause real quick and go through it with the class to see if we can do it together. Okay, so we want to get our direction of the B fields. We're going to use right-hand rule number 2 here, thumb pointing out because I1's pointing out at this position P. Fingers curl, pointing counterclockwise. So for it to be perpendicular to the shortest distance between them, that shortest distance being this guy. The only way it could be perpendicular was either pointing this way or this way, but which one curls in that direction? It'd be the one that is pointing up like this. So that is B1. Next for B2, this one's a little tricky, and that's mainly because of my fault, because the drawing is bad. But this is an equilateral triangle. And that means every single side is 60 degrees. 60 degrees. So what's the direction here? Again, thumbs pointing out, fingers curl, shortest distance needs to be perpendicular. It's going to be perpendicular to this line, something like this. And the reason why it's not directly on this line right here, well, that's because, remember, by definition, perpendicular is 90 degrees. So that means there needs to be this right angle right there. Okay? So to determine the direction the field is going to go, we can break this guy into its components. Well, what's the components for B1? I'll do that in green. No, I'll do that in blue. So B1 has, well, let me break this into its sides here. So let me just do this. Like this. So we know this one's 30 degrees. And we break into its components. This is going to be a B1 sine 30. And we'll have a B1 cosine 30. And then if we break B2 into its components, we'll have a vector pointing downwards, B2 sine 30. And remember, this is the angle for B2 right here. Don't get tricked because the 60's right here. It's really the drawing that's really bad. So it's the 30 right here. And we also have an X component, which is going to be pointing in the same direction as B1. So I'll say plus B2 cosine 30. Okay. So we're able to answer the direction that B field will be pointing before we even work out what the B net is. Can anybody tell me why? The y's cancel out. Great. This cancels out. This cancels out. So which of the only vectors that exist still are the two X components that are pointing leftwards? So A is left. In part B, we're asked to determine the magnitude of the net magnetic field at point P. This is now business as usual. B net squared is going to be equal to B net X squared plus B net Y squared. We already talked about that B net Y squared is equal to 0. So we just got to plug in everything for our B net X. So that's B1 cosine theta or cosine 30 plus B1 cosine, oh no, B2 cosine theta. And we can draw our coordinate system too. I guess I never did that. Okay, so we can obviously do a lot of factoring here. And we can factor out one of them entirely, actually, and we just got to multiply one out. Okay, this whole thing comes out to be 0.0000. That's 3 zeros right there, and then plus one more, so that's 4 altogether. 14T, and again, we already talked about why it's left. Okay, and now the last point is we want to determine the direction of the magnetic force on the wire that has the current I3. So this wire that's hanging out right here, what is the force there? So again, I must have forgot to include the length of the wire. So I'll tell you right now, L is equal to 1 meter. So we set up our equation. The angle between them is 90. We know the current there, 12. The length, I just told you, is 1. We know what the B field there is, it's gonna be 0.000166. No, I was like, wait, what? 1,4. Sorry, let me rewrite this. This is that B net we just solved for from the past one, okay? And we can draw this guy out now. So we know the direction the current's going. I'll do that in green. We know I3 is going out of the page. We know the B field is going to the left. So then we do our right-hand rule. Pointer finger going into the page, middle finger pointing leftwards, my thumb points up, thumb pointing up. So our answer is 0.000166 up. Oh, newtons up. Okay.